All right, guys, we're just going to keep trucking, and we'll do kind of a big test at the end rather than in the middle. Oh, we're real tight on time. Okay, we're going to talk about dilations today. This is when you change the size of something, right? So these are not going to be congruent. Okay, they're going to be similar. Okay, so the idea with that, right? If they're similar, they're going to be man, I'm running out of room here. The same shape, but different sizes, right? And different actually means in this case they're going to be in the same proportion as each other. Okay, so that's the idea here. So we've got this landscape architect. Let's call them Trish. They design a small splash pad represented by A, B, C. Then she decides to make the splash pad larger, as shown by A, D, E. How are the splash pad designs alike? How are they different? Well, let's do a T chart here. They're alike. Wow, that's real bad, Dave. Come on. A-L-I. There you go. Okay. And how are they different? Okay. Well, they're alike in that they're both triangles, so same shape. Okay. They're different in that they are different sizes, right? Okay, one is smaller, one is larger than the other, right? That's the big thing right there. Just going to zoom in on here. We can see this grid, right? A, B, C goes out to 2, 0, but A, D, E goes out to 5, 0, right? So we've got A, let's actually, okay. So A, B, C, and then A, D, E, right? Because A is common in between the two triangles, right? A is 0. 0, B is at 0, 2, and C is at 2, 0. Okay, and then for the other one, right, A is at 0, 0 and doesn't change, right? D is at 0, 5, and E is at 5, 0. So these are the kind of differences in the points right here. And you can see that if we kind of take literally everything here and multiply it by 2.5, we get that new result of 5, right? So if we take our original points right here and we take 2, because like technically these are all 0. So if we multiply 0 by anything, it stays 0. So that's why even though we're making it bigger, we multiply this by 2.5, it stays 0, right? So 2 times 2.5, let's just double check my math here. That gets us to 5. So if we take 2 times 2.5, we get to 5. So basically, we're making the new splash pad 2.5 times bigger than the old one. So that's kind of how we work our math right here. We're just multiplying by how much bigger it is, right? Okay. So yeah, that's the idea here. Okay, example number 1. The landscape architect designs 2 open green spaces for another area of the park. She designs the larger space so that the length of each side is 3 times the length of its corresponding side in the smaller green space. Where should the architect draw the larger green space? So you see how this is kind of washed out here? I did that because in the original it was a much more vibrant green, but you could not see the grid on there. So I kind of like washed it out a little bit so you could see the grid. So anyway, so we have this green space right here, A, B, C, D, and this is 1 by 2. Okay, now that's the smaller one, and we want to make the other one 3 times bigger. Okay, and so it's basically going to be 3 by 6 on the new one, right? And so since we have our grid right here, the idea is we're going to take our points here, so like A, B, C, D. The A is at, let's see, 1, 2. B is at 3, 2. C is at 3, 1. And D is at 1, 1. So the idea is we're going to take each, let's see, does orange show up on here? Yeah, that's fine. Okay, we're going to take each one and multiply it by the how much bigger we want it, right? So we're going to be multiplying by 3. Now that amount that we're multiplying it by, the variable we use for that is k, and k stands for scale factor. Okay, so the scale factor of this dilation, right? Dilation means we're changing the size. So the scale factor of this dilation is 3, which means we're making this 3 times bigger. And so what we do is we just take each number here and we multiply it by 3, and that gives us our new point, right? Our new points, set of points, right? So this becomes 3, 6. After we multiply each of these by 3, and then let's see, that becomes 9. Come on, 9, 6. Okay, and then 9, 3, and then 3, 3 for that. And then we just plot these points. D prime is 3, 3, so that's going to be right here and right here. Okay, 9, 3 for C. So 9 is right here, and then what's on 2, 3? So that's C prime. And then 9, 6 over 9 and up. Let's see, 1, 2, 3, 4, 5, 6. That's our B prime. And then last but not least is A prime at 3, 6, which will be right there. Okay. And where is my ruler? So now we have our secondary green space, and we can see that it is 3 times the size, right? Let's double check, right? So this side should be 1, 2, 3 boxes. It is, because that's 1, so 1 times 3 is 3. So we've got the right kind of side there. And then this is 2, so it should be 1, 2, 3, 4, 5, 6, right? Because 2 times 3 is 6. So we have our new larger open space kind of farther out in the park there. Yeah, that's the idea, right? You multiply your original shape, all the points of it, by the scale factor, and then it will either increase or decrease, right? And we'll see kind of examples of both the decrease and the increase as we go here, right? But anyway, your scale factor, right? So if it's bigger than 1, it's an increase. And if it's smaller than 1, so a fraction, it's a decrease. And so we'll see what that looks like. Okay, so we have f prime, g prime, h prime, I prime. So this guy right here is the image of f, g, h, I after a dilation with the center at the origin. Okay, what is the scale factor? So the idea here is you're just going to compare the original to the new one. You'll just compare sides, right? So this is 1 by 1. This one is 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5. So 1 times what is 5? 5, right? You can think about this as an equation, right? If I have 1 here and I'm multiplying by the scale factor and I get to 5, well, 1k is the same as just k, right? So your scale factor is 5. I don't really know why they chose k for scale factor. I know why they didn't choose s, because s's look like 5s, or mine do anyway, but they can. So yeah, k is scale factor. That's 5 times bigger than the original. Okay. Yeah, same thing. We're actually doing one rather than kind of figure out the scale factor. I've already got a chart for your A's and your A primes, and your B's and your B primes, etc. Okay. So A is, let's do A in orange actually. A is at 2, negative 2. Okay, and we're going to have a scale factor of 2 right here, so it's going to get twice as big. We're actually not going to draw this out. We're just going to figure out the points to it, right? B is 2, 1. C is 4, 0. And D is 4, negative 1. Okay, and then for the new shape, you just multiply each of those by 2. Okay, so this becomes 4, negative 4, right? If you have a negative, keep it. Okay, this becomes 4, 2, right? This becomes 8, 0, because 0 multiplied by anything remains 0, right? And this becomes 8, negative 2. So we could graph that out if we wanted to, but we can trust our math that this is going to be much bigger. It's actually going to send us off the grid. So that's kind of how you do the math right there. Okay. So again, we've seen scale factors of 3 and 2 and 5 so far, right? So those are all greater than 1. Okay. So when you have a scale factor that is greater than 1, it's an enlargement. Okay. And when you have a scale factor less than 1, it's a reduction. So you either enlarge or reduce. Okay. So when it's bigger than 1, it's getting bigger. When it's less than 1, it's getting smaller. When it's equal to 1, that means it's the same size because you're just multiplying by 1. Okay. All right. So what are the coordinates of the image of PQRS after a dilation with center 0, 0? So right there. And a scale factor of 1/2. So since we have a scale factor of 1/2, that's less than 1, we know we're getting smaller. Okay. So the idea here, right, we're going to have PQRS. Okay, we're going to, actually, let me just leave this in green. P is, let's see, 6, 10. Q is 10, 10. R is 10, 6. And S is 6, 6, right? So this is good because these are all even numbers. So our points will be not even numbers. Yeah, they're even numbers. So when we multiply one by 1/2 or divide by 2, it'll work out to whole numbers, right? So P prime, after we multiply each of these by 1/2 or divide by 2 or think what's half of 6 and half of 10, that becomes 3, 5, right? Q prime becomes 5, 5, right? 5, 3 for R prime. And S becomes 3, 3, right? Yeah, it's super simple, guys, right? You're just multiplying all of your numbers by a number, right? So now we've got 3 5s. So we go over 3 and up. 1, 2, 3, 4, 5. That's P prime. Okay. Q prime is right there. 5, 5. And then 5, 3 for R prime. And then 3, 3 for S prime. Okay. And so you'll notice that that is half as big, right? This square is 4 by 4. This square is 2 by 2. So half the size of it, right? One thing I do want you to notice, when you're reducing, your shape kind of moves toward your center, right? Typically, we're going to do the origin, right? So it's moving towards the center for reduction, right? But if you have an enlargement, you can see that it's growing away from it, right? It's going away from it, right? You can think about it like the Big Bang, right? The universe is expanding away from that point, right? The universe is getting larger and it's moving away from the center where it started. But you can think of like a reduction as like a black hole, right? Things are getting smaller as they're getting compressed as they move towards the center of the black hole. They're getting smaller and they dilate down. There you go, guys. This is going to go in our notebooks. Sorry about that. Okay, this is going to go on page 55. I like dilations. They're easy. And it's cool to make. Yeah, so maybe we'll have like a practice day where we kind of put them all together. There you go, page 55. We'll put it in our notebook here, right? So this is page 55. 6, 6, describe dilations. And so now we figured out all of our 4 transformations, our 3 rigid transformations that make congruent figures, and then our dilation non-rigid that makes similar figures. So there you go.